Let me record the session. Okay, we have 10 people online, and then we probably are expecting more, but we probably just go ahead and continue get started. So before I start with the actual session, just want to check if you guys get a chance to get the book and any difficulty finding a book, etc. It is expensive, that I know. Hopefully you find some solutions, such as getting a rent a version, or get a electronic version, etc. Okay, great. So that's great. Okay, good to know. If you haven't done that yet, please do that as soon as you can, because we already have one homework due this weekend, and then the homework is coming from the textbook, and then you need to read the textbook to understand a little bit more depth of the contents that we're going to cover in class. So that's why it's important that you have that. So welcome to the ISDA 609. This particular class was offered only in 4 semesters in the previous years, but we just realized the importance of the course. Number one, number two, there are many more students that actually join in the program in the past year, so we try to split to a 2-semester course, and then we're having it this semester as well as 4th semester as well. So I'm sure you're not the 1st semester student, so you're familiar with the format of the class. And also, just to remind you that if you look at the syllabus, we have 3 prerequisites. One is 600, the other one is 605, the third one is 606. So I think if you are taking 605 and 606 this semester, it should be fine. If you have taken it previously, that would be even better. And hopefully you have some basic statistics or probability courses previously. If not, send me an email or send me a message, and then we can discuss. Using the book. The book is really just for this course, but it captures a lot of fundamental concepts. So I don't really see it. You can probably use it as a reference in the future, but I don't think it's directly used for other courses. Okay, Aaron was asking whether the book is used for other courses as well, so I just answered. So if we continue with this, so basically we call this course as math modeling, and math modeling itself is really a branch of applied mathematics, and then it is considered to be part of the optimization. Optimization is part of it. So if you look at that, topics that will be covered include different systems of differential equations, linear programming, nonlinear programming, and algorithmic search methods for optimization, and integer programming, branch and bound, and their uses. So this is basically the snapshot of the course. So if you have never heard of optimization, you probably heard of something such as search engine optimization, marketing optimization, maybe ad optimization, but reality is they have some sort of elements of mathematical programming in there, but it's not quite the same. Especially search engine optimization is totally different from the optimization here that we're talking about. If you remember that in high school or in college, you studied how to find the minimum point of a quadratic function. That's really an optimization problem. And then if you look at here, the topics here, The first one that we want to mention, linear programming itself, is saying that the program itself, the math program itself, is linear, meaning that in every single optimization problem, we always have an objective function. In addition to that, we have a set of constraints. And then if the optimization objective function is linear and also all the constraints are linear, then we call it a linear programming. And then we will go much more depth in the class. And then here I just want to give you a brief introduction here. And also just to remind you, in the week one, not in week one, it's actually in the getting started in that page of the Blackboard course site, you would find that I recorded some sort of video around 10 to 15 minutes. 15 minutes actually. I think it might be helpful for you to go through that part so that you would get a really good understanding what this course is about, what it is about for this course. And then in the whole semester, we're going to go through all the major topics that was mentioned in that video in depth. Okay, and then look at the course learning objectives. We're going to study linear programming. And we're going to formulate. We're going to formulate LP models, which is linear programming, and use simplex method to solve it, and understand duality and be able to perform some sort of sensitivity analysis for the LP model. And in addition to that, you would study integer programming and understand and apply branch and bound techniques. You would get an introduction on quadratic and nonlinear programming models and understand the second order condition and apply to quadratic programming, learn steepest descent method. And then you would realize that in many of the machine learning algorithms, the math problem itself is a quadratic programming or nonlinear programming problem. And then you would be able to learn how to use commercial and free optimization tools. In particular, in this course, we're using R, and then you can use some of the R optimization packages to solve some of the homeworks. But I just want to point out that for the first time, if you use simplex method to solve LP model, you have to solve it by hand. You cannot use a computer to solve it directly. But after the first homework, first assignment, I'm not talking about assignment 1, but I'm not talking about the problem that will be solved by simplex method. First problem it would be somewhere in week 6 or week 7. Just I'll let you know when it comes to that point. And then the basic programming learning objectives, essentially the same thing. We want to build a very solid fundamental understanding of these math programming problems, and to prepare you to have the basic skills to do data collection, data cleaning, and then build some sort of models to make sense out of the data, and then try to get some sort of conclusion out of data. And then you will be able to evaluate your model, be able to talk about the key points of the model, why it works, why it didn't, and then to also to point out what's the potential ways to improve the model. And then after you study the material of the course, at the end of the semester we have a course project, and then that would be really when you can apply all the skills and put them together. Hopefully you can learn something from the whole process. And then just some assignments and grading. So note that we have participation here, online discussion forums, and communication with fellow students. This is consists of the final score, final grade of 14%. And then you have to submit, as if you look at the first note here, please actively participate in online discussion each week about the homework, some discussion forums that the instructor provided, or projects. Please have at least one substantial discussion, express your views on the topic in discussion extensively. Can be a reply to some other students' posts. You don't really need to say that you have to invent your own, come up some new things. You can be continue. It can be a continue of some fellow students' discussion, but hopefully it's not just one sentence to say yes, I agree with this point or great point. Something like that wouldn't be considered to be substantial. But would the three sentences be considered substantial? Maybe, right? It really depends on whether you're trying to express some sort of view. Okay, so this is 14%. We have probably around 10-week discussion, so it's really, I consider it to be 3 points for you guys. As long as you try to actively participate, I don't see any issue that you would not get that. And then assignments. It looks like it's a lot. Yes, it is a lot. It's 14 assignments, and then it's equally weighted. So essentially saying that if we have 15 to 17 weeks of the course, and then you almost have the one homework every week, and then the last three weeks you probably would be dedicated on your course project. So homework, we have a lot of homework here for this particular course, even though good news is we don't have any exam, we don't have midterm, we don't have final exam, so it's only assignments and course project. And then course project consists 30% of the final grade. And then I have a little bit discussion here on the course project. So roughly, you have to submit a project proposal draft by end of week 9. And then I will try to provide some feedback. Maybe your scope is too large or scope is a little bit small. And then I'll try to give some suggestions so that you can finalize it by the end of week 11. And then each of those two would be worth 10% of the project grade. And then project presentation slides due on the date that we are going to present, which is half an hour before the presentation starts. And then presentations would start on May 18th. Mark the date if you need. And it's Wednesday, worth 30% of the project grade together with your project presentation slides submission. And then final project report on the same week, end of the week, which is May 22nd, worth 50% of the project. Great. So if you say that, okay, my final project is not ready yet, but my slides is ready somewhat, at least you can present the slides first, and then you can try to finalize the project. Maybe you can further improve based on fellow students' suggestions, and then try to finalize in the last couple of days of that week. That's the plan there. And then, as I mentioned in an email that I sent earlier, this is a required textbook. And then we have a supplementary text. Fortunately, this is an online textbook. You really don't need to purchase this textbook. I talked to Professor John Chinek and got approval from him to use this online text, which is nice. That's pretty much of the textbook. And please download R. Probably you already have that. And then we probably will need to use some different. We need to use some different packages throughout the course. I will point out to the right packages as the course goes along. Actually, just want to mention one more thing for the assignments. Yeah, just forgot to mention here. Please do not submit your homework by email. Submit through Blackboard system. for each of the homework, you only need to finish 3 of the selected problems. So if you look at the problems that I assigned for week 1, for example, you probably have 5. And then if you can finish 3 of them, that would be great. And then if you want to finish, take an extra step, try to finish a little bit more, you can up to 20% bonus of the homework. And then here I didn't write specifically here, but I allow you to submit your homework late for 3 times throughout the semester. But you have to let me know before you are going to be late, right? For example, this week you say, okay, I cannot make it this week because of my work schedule, because of my family issue, etc. And then you say, okay, I will try to submit next week along with homework too. And then you can let me know. But I allow give you 3 opportunities to do that throughout the semester. That's something that I probably will write an email to you guys later today or later this week, so that everyone is on the same page. And then if we continue here, this is my contact information, my email, and send me an email if you have questions. You can also try to ask questions through the Blackboard system or try to answer in the Blackboard system as well. And then let's look at the outline of each week. So you would say that we try to follow the textbook rather closely. And then for the couple of weeks, for the first week, I would say that for the first 3 weeks, it really don't have a lot of substantial contents there. And then starting from week 4, we have introduction to simulation modeling, etc., with probabilistic modeling followed by LP, and the modeling using graph theory, modeling using decision theory, followed by game theory and differential equations, and systems of differential equations, nonlinear programming, graph as function as models, and integer programming. So that's pretty much the snapshot of all the contents that we're going to cover. And then you can see that I mainly followed this particular textbook from our required textbook, George Daniel chapters. And then the integer programming itself is from Chinek. That's week 14. And then we have week 15, week 16 is supposed to be 16 here. So week 16 and week 15 to finish the final project, even though you actually started working on the project probably 2 or 3 weeks earlier than this particular time, which is week 19. So that's pretty much the plan for the semester. Have to be really because the school specifically stress the importance of academic integrity. So I want to mention here, you have to be really pay attention to the policy. Academic dishonesty is unacceptable and will not be tolerated. Cheating, forgery, plagiarism, and collusion in dishonest acts undermine educational mission of the City University of New York and the students' personal and intellectual growth. So just pay attention to that. But in a Blackboard system, you are allowed to discuss some of the questions. If you say, oh, I'm a little bit confused by this problem, I think it should be this. Is my understanding correct? And then if other students reply, yes, I have a similar understanding, etc., I think it should be fine as long as you don't actually post the code or solution. You can post some sort of pseudocode if you want, or outline of the solution. That's fine as well. I encourage the discussions, in other words, but don't put the exact solution that you have there. So that's that part. This is the last page of the syllabus have a more detailed description of the project. I'm not going to discuss in length today, but we're going to discuss sometimes around week 7, week 8 of the semester. Just a quick comment there is each team can consist of 2 or more members. Of course, if you want to work on something, if we want to work on something by yourself because of any reasons, maybe the schedule doesn't align with some other fellow students, or because the specific interests that you have cannot find some other students who would be interested in that topic, then you can do that on your own. That's not an issue at all, but we can discuss the possibilities of narrowing it down instead of scaling it up in terms of the scope of the project. And then okay, Sekha just asked, can we discuss the solution of non-homework problems? Yes, absolutely. You can discuss in this Blackboard, you can discuss anything that you want, you feel comfortable. Yeah, that's definitely encouraged. And also from my end, I'm trying to compile some sort of solution for all homework problems. So that way, if you only worked on 3 out of the 5, you can still look at the other 2, my solution for the other 2 problems to learn from there. That's the plan for this semester. So do you have any questions from your end so far?
Hi. Yeah, I do have just one question. I know we're probably going to touch on it a little bit later, but regarding the project for end of semester, so what's typically required there? So is it more just identifying a mathematical model, and then building out a computational model that proves it out?
Yes, maybe we can quickly, yes, that's basically the idea, but we have a couple of options, right? Option 1 is select from the projects from the textbook, and then option 2 would be something that if you think something is really of great interest to you and you have a way to get the data, then you can get that as well. And then in terms of the way that you do, you would yes, you could formulate as a math problem and then try to solve it using R and then discuss the results with the students. And then at the end, so essentially that report would be consisted of these components. 1, analysis of the problem, the methodology that you use, details of the methodology, and the findings from the project. And then number 5 is, are they different from your initial expectation? If so, is there a suitable explanation? If different, what potential way that you can improve the methodology? So that's basically the idea, so that you can put things together, you can express the problem and try to solve the problem.
Right. And then for the homeworks, do you prefer R markdowns as the submitted thing, or do you want PDFs or what?
Not really. Actually, I forgot to mention there. You can submit a PDF, right? After using R Markdown and generate PDF, you can using R Markdown generate HTML, and then I even allow you to do something like you can, if for some of the problem really just mathematics, you don't need to type them. If you write on a piece of paper, you even handwriting, and then you take a picture, that's fine too. But just don't, yeah, just don't send, if 5 problems, you have 10 pages, don't send me 10 different JPEG files. Put them together as one zip or some, maybe as one file, and then submit through the system. That would be more preferable.
Nice. Yeah, I knew I was going to like this class. Thanks.
Okay. I think I should mention that somewhere, but maybe not. It's not here. It's somewhere. I remember that I mentioned that somewhere on the Blackboard system. If
Yeah,
not,
yeah, are you gonna put the meeting times up on Blackboard as well? I don't think they're there. I just saw this in the email.
um, it's actually there. I believe I put it on Monday, so we can quickly go through together because we need to go there anyway.
Thank you.
No problem. So let's say, yeah, meetups in this particular page. That's the date that we're going to meet.
Okay, cool. Thank you.
Okay. And also we have office hours, which happening in the alternate weeks. So meaning that if we don't have a session next week, next Wednesday, which is February 10th, we would have an office hour starting from. Oh, this is wrong though. It's supposed to start at 8, I believe. But I'll confirm. I believe I got an email from. Yeah, this is wrong. Should be starting from 8 o'clock. I'll correct that and then also let you guys know. Yes, out week Wednesday, that would be 8 to 9, and then we have office hour 8 to 9, when there is no regular class in our week, and use the same login. And because this is the first week, if you haven't read if you haven't viewed this video yet, please do that. It's just an introduction of the course. And then this is a curriculum map that helps you understand where this particular course actually stands in the whole curriculum. And then take a look at the syllabus that we just went through, and then download your R. Course site navigation, you would see that we have announcement, getting started, which is this page, and then a little bit information about myself. And then you can go through the weekly materials and discussion board and meetup. So for the discussion board, I want to navigate a little bit. Okay, I didn't even see this email, this one yet, but I'll try to answer later. Okay, and then if you look at this would be the discussion. Week 1 discussion, for example, looks like everybody already published. Yeah, what I was saying that you could just reply from this same thread from here to continue, so that I would just review instead of going through here one by one. Either way would work. If you want to open a new thread, that's fine too there. Okay, that's there. And weekly materials. So if we look here, I put all the PowerPoint that we're going to cover for each week into one file. It's there, so you can download all of them if you want to. And then there's a little bit more discussion of course project. We can discuss more further detail a little bit later. And then for each week, you just go to the specific week. And then even though there's a brief introduction there as well, you can take a look there. Especially for the week that we don't have a course. Sometimes we wouldn't be able to cover the week before. Then you would want to view that video if you can. And then that's week 1 material PowerPoint and discussion board homework. For example, here this week we have actually 4 problems. You're expected to see 2 of them. Solution, apparently you don't see that yet. I purposely not published them yet, and also I'm in the process of trying to consolidate the solution to hopefully it's a better version this semester. Okay, so that's that. Okay, we actually we have a section probably today. We probably want let's say we have a section that everyone explains. I mean, try to try self introduction. So if we can quickly go through by yourself if you want to, and then we probably won't go through here in the class. And then I know some of you already took not a lot, but already took the maths last spring, the computational mathematics class from me, and then the rest, many of you actually are new faces for me, and then we can go through the text. Go through the materials together this semester for this math modeling. Okay, I'll go through the list myself as well. Right after this, actually, this session. So, do you have any other questions so far? Okay, no. If not, let me continue to put up the slides for the first 2 weeks. Relatively speaking, the first 2 weeks are materials light. So, but be prepared. It can get really intensive sometime after the fourth week. So, and then it needs a lot of effort for this particular course to understand all the materials. Okay, so just bear with me 1 second. I'll get started in like 10-15 seconds. Okay, so let's continue. So this is week 1 material. So before you start reading the book for week 1, please definitely review the integration techniques in Appendix D, page APP-12. And then review the contents in the Appendix D. Make sure that you are comfortable with these math techniques. Ask questions if you have any, either through Blackboard or email. So the integration mainly just because it will be used for the differential equations problems. As you can see there, 2 weeks of the materials actually cover the differential equations. So it's important that you know to brush up on this aspect, which is actually college calculus. So I believe you probably have already learned before. Just make sure that please do that. Okay. Okay. Actually, I just saw a question. saying that be able to include the specific due dates instead of end of week for the homework are wrong. Actually, if you look at here, this outline, end of the week Sunday essentially is February 7th here. So this one, end of week is February 14th. So you would know that if you look at the calendar, 7th would be Sunday, 14th would be Sunday as well. So essentially it's there. Hopefully that doesn't bring up too much inconvenience for you, but it's really there just because and also in the Blackwell system, if we go back a little bit, you would see that it's February 7th. Here we don't have, but I just hope that you can use that syllabus as a reference there. Also here in each week, you would see that one is the end of the week. Okay. Okay, let's continue with this, and then regarding the review of Appendix D, yeah, please do that, and then continue to read week 1 material after that. And then what's in there, it has U substitution, integration by parts, rational functions, partial fractions, distinct linear factors, a repeated linear factor, and quadratic factor. What we really use is really just the first 2 parts that we have here in the Appendix D, but it doesn't hurt for you to review the whole thing if you want to. And then Chapter 1 is specifically named as modeling change. So it has some introduction and how to modeling change with difference equations. It's difference equations, not differential equations. That's number 1 that we need to pay attention to. And then approximating change with difference equations. It's relatively straightforward. We are going to go through that shortly. And then there's some discussion on solutions to the dynamical systems and also systems of difference equations, followed by the homework. So let's take a look at the flow of methodology, a modeling process. So what is a model? We start from the real world data. Hold on, I'm just trying to find some sort of pointer. Mm-hmm. Didn't see that. But anyway, so we really what we're really looking at is starting from real world data. We try to simplify the problem and then try to build a model. And then through analysis, we come up some sort of mathematical conclusion, which is the third box in the graph. And then we try to interpret the mathematical conclusions, trying to do some interpretation, and then beyond that, we start prediction and explanation, and then go back to the real world data, try to verify your predictions. And then if we go to chapter 4, week 4 for simulation, it's a little bit different than this process, and then we are going to explain why in some cases simulation would be useful, in some other cases math modeling would be useful. And then here we want to see one thing is a definition that if two variables y and x are proportional to each other, if one is always a constant multiple of the other, that is y equal to kx. Uh, we, I believe you probably have come across linear regression in some regard, which would be y equal to kx plus b, and then using real world x data of x and y trying to calibrate that k and b, right? So, but it's really very similar. And then in this particular course, we're going to learn what we're going to learn is linear regression itself is a quadratic programming problem, and then it can be solved by some of the optimization methods that we discussed here in this course. And then how to modeling change. It's really just future value is equal to present value plus change. And then if we continue for a sequence of numbers, A is a set of A0 all the way to AN. And then the first differences are delta A0 is A1 minus A0 delta A1 equal to A2 minus A1, so on and so forth. And in high school, you probably studied the constant change sequence. So it's really similar to that, except that here we didn't say that delta A0 equal to delta A1 did equal to delta A2, etc. So for each positive integer n, the nth first difference is delta an equal to an plus 1 minus an. And then graphical representation of this one is saying that, okay, at period n, the point is really at an, and then at period an plus 1, the point is at the value of y is at an plus 1. So the time period difference is 1, and then the y value change is delta an equal to an plus 1 minus an. And then we can use this simple difference model to study the mortgage in a whole. And then the payment for the next period can be modeled. Now, the here is really trying to do is the balance of the mortgage is can be modeled this way, which is equal to previous balance plus some sort of interest minus the principal payment that you have already made, which is in this case used $880.87 as that constant, and then you have to initialize your function which starts at b0 equal to 8,000, and then you can estimate how long this can be paid off. And then how to model change with different equations. A sequence is a function whose domain is a set of all non-negative integers and whose range is a subset of the real numbers. And a dynamical system is a relationship among terms in a sequence. A numerical solution is a table of values satisfying the dynamical system. So the book actually mentioned how you can approximating change with different equations, saying that the basic idea is this change is delta an in a specific period equal to some function of s. And then two examples here. One example is delta pn equal to pn plus 1 minus pn equal to 0.5 pn, which is this is a proportion that we discussed earlier, which essentially saying that the delta is a k times previous value and k itself is 0.5. And then another example here, delta pn equal to pn plus 1 minus pn equal to k 665 minus pn times pn. and apparently you can see that the first one is proportional, linear proportional to the previous observation, but the second one you can see it's no longer linear, it's a quadratic proportion to previous value, right? It's k times some function of k times pn and some function of k times pn squared in that case. And then graphically we can represent that change in this way. And then the homework is closely related to this particular this sort of a relationship. It's rather simple in some regard. And then the book tried to say that if we try to model that way, let's look at the observation versus prediction. And then predicted value is in empty dotted line, but a dotted spot, and then actual observation is actually solid spot. And then you can see that relatively speaking, the model is doing a reasonably well job. And then you should later on we would learn how would you measure how good the model is, right? You probably want to use some sort of metrics. Maybe so, for example, mean squared error that we discussed in the computational mathematics course. Maybe some other sort of metrics that you can use to measure the effectiveness of your model. And then the method of conjecture powerful mathematical techniques to hypothesize the form of a solution and then to accept or reject the hypothesis. So you look for a pattern, you have some sort of assumption or conjecture, and then try to test the conjecture and then conclusion. Linear dynamical system. The solution of the linear dynamical system is an plus 1 equal to Ran for R. Any non-zero constant is ak is r powered by k times a0. So where a0 is a given initial value. That's a linear relationship because ak and a0 have a linear relationship, even though r powered by k is still a constant. Right? And then a number a is called equilibrium value or fixed point of a dynamic system. For this particular function, if ak equal to a for all the k equal to 1, 2, 3, etc. When a0 is a, that is ak equal to a. It's a constant solution to the dynamic system. So it's saying that for example, if you look at the equivalent value for the following system, an plus 1 equal to Ran plus b is really a equal to b divided by 1 minus r. So it says that if r equal to 1 and b equal to 0, every number is an equilibrium value. If r equal to 1 and b not 0, no equilibrium value exists. The book itself actually has more detailed discussion here for this particular example for linear dynamic system. Our homework touches upon this one as well. And then nonlinear system, as I mentioned earlier, an plus 1 is a quadratic function of an instead of a linear function there. And then there's some very good examples there. I really actually encourage you to go through them, even though you probably, if you have time, go through all of them. If not, at least go through 2 of them so that you can get an idea on what's the application of the topics that we're trying to cover. And then just want to mention that these examples will be discussed in much further details using other methods later in the course. So make sure that make sure that you can understand these examples. If not, pay attention to sensitivity of initial condition. If not, apparently I'm missing something here in this second bullet here. But pay attention to the sensitivity of initial condition, which is important in math modeling. The stability of the solution from the model, which is the sensitivity discussion. That's the homework for chapter 1, and that's the homework for this week. So again, you only need to finish 3 out of this 4. And then if you can finish the extra homework, that would be great as well. So let's continue with week 2. So what we are covering for this week is including mathematical modeling using proportionality, modeling using geometric similarity, and there are 2 examples. One is automobile gasoline mileage. The other one is body weight and height, strength, and agility, followed by homework. So remember that in the previous week we discussed this chart on the left-hand side, on the right-hand side, which is a math model. Let's take a look at the left-hand side, the bottom of the left-hand side. So the only difference is we instead of doing some sort of real-world explanation or predictions, we're doing real-world conclusions by observing the real-world behavior. So if you look at the top chart of the left, real-world systems is really observed behavior of phenomena. But on the right-hand side, we see mathematical world is real models, which mathematical operations and rules, mathematical conclusions. So the real difference is it would be nice if we can observe everything in real world. We look at real world behavior and come up with some sort of real world conclusions. Unfortunately, we cannot observe all the behavior, all the phenomena. That's the exact reason that we need to build some sort of math models, especially for data analysis for statistician. We're trying to sample from the population to get a sample and then use the sample to some sort of inference. That's the whole purpose of building the math models. So you can see here, one key part is how we can use real world to verify our model results instead of using real world, real behavior observation to do some sort of real world conclusions using some sort of trials there. So that's a difference between real world systems versus mathematical systems. And then in terms of modeling itself, you can see that from the top table chart, you can see that there are 2 ways, as we just mentioned, right? We can do mathematical representation or replication of behavior. And then for mathematical representation, which will be the focus of this course, you would do model construction, you run some sort of analysis, and then you need to select from the right model. You may have multiple forms of ways to model the same problems. At the end, you have to select the right model, which is the model selection branch there. And then in terms of replication of real world behavior, you can do 2 things. One is you do experimentation. The second thing is you do some sort of simulation. So you can see that math model itself and simulation is some sort of different, in some sort of different realm of approaching the same set of problems. The basic rule of thumb is if you can model the problem rather accurately using some sort of math model, you probably don't want to use simulation. but in many of the cases, the problem is so complex, or the dynamics of the components is so complex so that you cannot use a math model to accurately represent the relationship. You would have to use simulation to understand the overall behavior. For example, in a queuing specifically in the checkout system in Walmart, for example, or Target, if you have 5 servers in the checkout counters, and then you can model the problem as some sort of queuing system stochastic process that we are going to discuss somewhere in week 8 or week 9, I believe. And then it's tractable, you can solve it. But if the and when we model that problem, we have many assumptions there. One is the arrival of the customers. The second one is the service time of the checkout counter. And then the third thing that you actually assumed is something like first in, first out, which is very reasonable in some sense. But in some other cases, if someone wants to join a different queue after waiting 3 minutes, he said, okay, my the counter that I'm currently waiting for is just too slow. I need to hop on a different line. That type of behavior, mathematically, it's rather difficult to model. So in that case, simulation would be very helpful to understand the throughput of the checkout counter. How many customers can a particular checkout counter serve in a certain period of time, and time in the queue, time in the checkout counter, etc. That would be really useful when you use simulation. Just to give you a sense there. And then let's look at compare among the model types. So we have many dimensions there, right? We can look at real world observations, which if you think about what we just discussed there, right? In terms of fidelity, apparently real world observations are more reliable if we have a reliable way to measure the data. And some of the models might have issues to represent the real world observations. And in terms of cost, real world observations is apparently more expensive. Sometimes it's prohibitive. It's impossible for you to observe to get a lot of real world observations, right? And then selecting models might be relatively easier. And then, but in terms of flexibility, we can see that apparently mathematical models itself is winning here from this dimension. That's why it does have its own merit. And then in terms of simulation, in terms of cost, fidelity, cost, and the flexibility, simulation is really in some way in between. And then this is relatively speaking straightforward, but I still want to give you a more concrete explanation here. You need to identify the problem, you need to make assumptions, and then what assumption you make. Identify and classify the variables, determine interrelationship between the variables and submodels. Just as I mentioned earlier, for the checkout counter at Target, this particular example, you have to make certain assumptions regarding the inter-arrival time of the customers who would line up in the waiting line and then trying to check out, and then the inter-arrival, the service time distribution for the particular server. It would be different for every single server for sure, and then you have to somehow to make some sort of assumption. Sometimes what you could do is you make real observations and then try to fit the model, fit the distribution fit the data with a specific distribution, and then you have certain confidence about your submodels. Once you have those submodels, you put them together, try to solve the whole problem. That's the importance of step 2, making assumptions. And then step 3, you solve the model. Step 4, verify the model. Does it address the problem? Does it make common sense? Test it with real-world data. And then step 5, implement the model. Step 6 is maintain the model. So step 5 and 6 is really more from a business practice perspective. In terms of really trying to build a model is 1, 2, 3, and 4. And then, as you can imagine, it's really an iterative nature of model construction. It doesn't just say that you need to finish 1, 2, 3, 6, and then it's done. It's always an iterative process, maybe coming back to step 3 or come up with new assumptions of step 2, and then further improve it. It's universal, not only in academia, but also in business practice. And then here it says the art of mathematical modeling is trying to simplifying or refining the model as required. And then model simplification, you need to restrict problem identification. You probably want to ignore some variables. You want to combine several variables together to have a new variable. And then you need to set some variables to be constant. Assume simple linear relationships, and also possible to incorporate more assumptions, as you can see. And then how to refine a model. You expand the problem, consider additional variables, consider each variable in detail, allow variation in the variables, consider nonlinear relationships, and reduce the number of assumptions. That's a model refinement. But as you can see that there's no clear cut. Is it going to say that, is it going to be say, okay, if I have a linear regression model, I have 100 variables, I explain 98 of the variance versus I have 10 variables, I can explain 95% of the variance of the data. Probably the latter would be better, because even though it has less proficiency in terms of the explanation of the real data, but it only used 10 variables versus 100 variables. If you think about the feasibility of trying to collect those 100 variables going forward, right, it probably makes more sense to select the 10 variable model instead of 100. So there is a paradox between model simplification and model refinement. Here is something, it's more like art that you can make a decision on later on in your real world of applications. In other words, it's not necessarily to say that the more complicated model, the better. It's probably more fair to say the more effective the model is, the better. Okay, we actually discussed this already, proportionality, y equal to kx, and then we all know many examples that you know in physics, like Hooke's law, Newton's law, Ohm's law, all are proportionality um, uh, examples, even though some of them could be linear, as we saw that in the equation 2.1, but many of them are nonlinear. You can see from 2.2, 2.3, 2.4, and then which one might work better. It's really depending on the data itself and some sort of experiment. And then in chapter 3 here, we want to mention that we're going to learn how to fit a linear model, which is really the linear regression. And then later in chapter 6, we will explain how the linear regression is connected to linear programming, linear optimization. No, actually, it's nonlinear optimization. I apologize for that. So how to connect a linear regression model with a quadratic programming problem, which we covered probably in week 9 or 10, actually a little bit later on in the course. And then modeling using geometric similarity. So in the textbook, there's some examples talking about raindrops from a motionless cloud, and then look at chapter 2.4, 2.5 for very good case studies on these topics. It's not crazily important, but it's definitely something that it's good to know. And then for next week, you have 5 problems to work with. You can select 3 of those 5, and then it's due next Sunday, which is the 14th. And then the first homework is due this weekend, which is 7th. That's pretty much that I'm going to cover today. Do you have any other questions so far? Homework 2 is due next week, February 14th. In terms of the logistics, because this week is the first week, in case you don't have a textbook, send me an email. Maybe I can give you a little bit of stretch so that you can finish the homework next week. This one will not be counted to the 3 out of the whole semester that being late policy. Okay, so if you don't have any other questions, we can stop here. And then hopefully you can learn something this semester from me, from the textbook. And then you have a great semester. And good night.